Dan, thanks for coming on. Really appreciate you taking the time to have a conversation with me. Would you mind telling us a little bit about yourself before we get started?
Sure. So I'm a professional scientist. I work at the Fermi National Accelerator Laboratory, and I am a professor of astronomy and astrophysics at the University of Chicago. I study things like particle physics and cosmology, the early universe, how the universe has evolved and changed over time, what kind of stuff we find in the universe. One of my specialties is something we call dark matter, which we're still trying to figure out. So yeah, that's the sort of stuff I do for a living.
Awesome. So what are you researching right now?
Oh, right now I've got a bunch of irons in the fire. I just finished a project talking about how we could use future gamma ray telescopes to look for these things called pulsars in the galactic center. I'm finishing up a thing where we're proposing a new dark matter candidate, like a new kind of hypothetical particle that might make up the dark matter. I'm working another project talking about whether large numbers of black holes might have been formed in the Big Bang. So kind of a lot of different things all at the same time.
Awesome. New candidate for dark matter. What is that? WIMP's not your favorite?
Well, this would technically be it's kind of on the border of a WIMP. So WIMP is a big umbrella term. And yeah, they kind of are my favorite, but not everyone agrees with me these days. What we mean by a WIMP is some sort of big, heavy particle that was created in the Big Bang. And those sorts of things have long been the favorite class of particles that we have hypothesized for the dark matter. There are other ideas, though, too, and nobody's particularly partisan in this game. We're all pretty open-minded about what it might be. This new candidate is produced in a little bit of a different way than a traditional WIMP, so it behaves... we don't really have a word for it, but it behaves a little bit differently.
So for the audience, what is dark matter?
Good. So a huge variety of different observations tell us that most of the mass in our universe is not made of ordinary stuff. It's not made of any combination of atoms. Instead, it's made of something else that doesn't appreciably radiate, reflect, or absorb light. Okay, so we can't see it, at least with any existing telescopes. What we do detect is the effects of its gravity. So, imagine, I don't know, the planet Mars was completely invisible. You can still figure out Mars was there by noticing that its moons were orbiting around this point in space, right? So we do something like that with dark matter too. We look at galaxies, and we look at how fast stars are in orbit around those galaxies, and it's way too fast for us to be able to account for with ordinary visible matter made of atoms, stars, gas, and dust, all that stuff. So something else has to be there to supply that gravity. We also see the effects of dark matter in the dynamics of larger systems that we call galaxy clusters. We see the effects of dark matter in what we call the cosmic microwave background, the light left over from the Big Bang. We see it in the shape of the large-scale structure of our universe. Kind of everywhere we look, we see evidence of dark matter, even though we really don't know what it is yet, other than something that doesn't appreciably interact with light.
So essentially like black holes, it doesn't really absorb, you don't really see it, but it causes lots of different effects that we see. But black holes are not enough to explain that, right? It's significantly more than black holes.
Well, the normal kinds of black holes that come, as if any kind of black hole is really normal, but whatever, the most normal kind, the kind that we're sure exists, the kind that are produced when stars collapse, or even the supermassive black holes we find in our own galaxy and other places, these can't be the dark matter, at least not very much of it. There is a very special range of masses of smaller mass black holes. These would be like somewhere between the mass of a small planet and a large asteroid. In that range, all the dark matter could hypothetically be made up of black holes. We're trying to find ways to test that hypothesis, but we haven't ruled that one out yet.
Can black holes that small exist?
They could. They would have to have been formed in the very early universe, before the first second or so after the Big Bang. But it's at least possible, though we have no evidence that these things exist, but we can write down theories that would cause a lot of black holes in that mass range to be generated. They're a bit complicated and like maybe not the most compelling of all theories, but they're a possibility.
And you were mentioning that you have a new kind of almost WIMP that you think you're positing explains them.
Well, so before that's made out to seem like it's a big deal, let's just keep in mind there are hundreds or thousands of different particles that have been hypothesized to make up the dark matter. It's not even hard to write down a new one. it's hard to write down a new one that is compelling on various axes, like ones that solve other problems and have different kinds of characteristics or different ways of looking for them. That's what we're really looking for. I mean, I can give you a new dark matter candidate every day before breakfast if you want, but it won't be very interesting. This particular one is interesting because it's it combines two existing theories. We think from the fact that these particles that exist in the universe called neutrinos, these particles have a little bit of mass, that there must be these other kinds of heavier particles called sterile neutrinos that must exist. And maybe they could make up the dark matter, and people have explored that. And it turns out that that doesn't work very well anymore. It used to work a lot better, but it doesn't work very well anymore. And on the other hand, there are these other theories, which we call twin Higgs theories. And in twin Higgs theories, you have certain dark matter candidates that come out, but turns out those don't work very well anymore. So what we're doing is working out whether there could be sterile neutrinos in twin Higgs theories that solve all the problems all at once and make for a good dark matter candidate. So I know that's a little bit inside baseball there, but that's what I was thinking about literally the last few days.
And why don't those particular theories individually work well anymore? Because you said they don't work well anymore. Because why?
Well, the scientific method is all predicated on you take a theory, you work out what its predictions are, and then you see if those predictions bear out. Most of the time they don't, that's just the nature of science. And when they do work out, you're surprised and happy, but usually they don't, and you can cross one more theory off the list. In the case of sterile neutrinos, we've been looking for signals using X-ray telescopes for a long time, and they have not been forthcoming. And we have been looking for the effects of that kind of dark matter on the how many small galaxies there are, and that does not agree with a lot of these predictions either. So slowly over time, more and more of the examples of this sort of theory have been ruled out. I wouldn't say they're completely, all the way ruled out now, but the data don't look good for these theories. On the other side, the twin Higgs side, there are big underground dark matter detectors. So these are devices in deep underground laboratories designed to look for those occasional instances when a dark matter particle comes and hits your experiments and kind of bounces off, leaving a transfer of momentum or a recoil or something. And, these theories generally predict that you should see enough of these events to have detected it by now. And as these experiments have gotten bigger and more sensitive, well, these theories have been increasingly under tension, probably approximately ruled out at this point.
Because we still haven't detected anything from those detectors.
That's right. Right. Nothing but silence so far.
And what are they looking for? What could other things interact with the dark matter detectors, like neutrinos? Could they cause the atoms? Because imagine they're using big pools of something and waiting for it to decay because it gets hit by something else. Is that about right?
Yeah. So actually, neutrinos are kind of a thorn in the sky, in the side of these detectors. They're getting big enough now that neutrinos start interacting, creating essentially a background noise that they have to overcome. So I would say that these detectors are going to get, 10, 20, 30, 40 times more sensitive than they presently are. And then they're going to hit a pretty hard wall. And those neutrinos are going to make it hard to become more sensitive to dark matter than they presently are. So one scientist's signal is another scientist's background. The neutrinos are the target of a lot of investigations. But in this case, if you're a dark matter hunter, you wish you could just turn off those neutrinos and make them go away. And you can't.
Efont asks, can you explain how dark matter detectors actually detect?
So there are a lot of different kinds of dark matter detectors. I don't want to give you the impression that there's just one. But like the leading one right now is an experiment called LZ, which stands for Lux Zeppelin. Two different experiments called Lux and Zeppelin merged to make LZ. So this is a big tank, a liquid xenon. So way up in the high numbers of the periodic table, you'll find xenon. It's a liquid noble gas, or in this case, it's a noble gas, but in this case, we keep it at temperatures and pressures where it's a liquid. This tank is kept underground at the Homestake mine in South Dakota. And it's instrumented, so if one of atoms atoms gets hit by something, just like the way you'd hit anything with a hammer or something, that energy imparted into it will generate things like little bits of light and little bits of freed electrons and things like this, that this instrument could tell are present. Okay, so that's extremely sensitive device. And most of the dark matter particles travel through the Earth and through this detector without anything happening. But one out of a very large number can actually hit an atom in this tank of xenon, impart just a little bit of momentum and recoil, create a little bit of light and charge. The instrument sees that and it goes, maybe this is one dark matter candidate. And you run this thing for years. You count how many times this happened and look at the properties of all those events. And you do one of two things. Either you say, well, I guess dark matter doesn't interact at least at this level, okay, at a certain rate. Or you say, oh, we have a bunch of weird events. Maybe it's dark matter. Let's investigate that further.
And why do you think we haven't seen dark matter? Why do you think it's so elusive?
I mean, the short answer is, we didn't know going into this how much this stuff would interact, right? So we had plenty of guesses or hypotheses. Some of those hypotheses says we should have seen it a long time ago, and we haven't. So we can now cross those off the list. And as time has gone on, we're left with more and more feebly interacting candidates left on the list. And those are the kind of last hypotheses standing, and we're going to continue to try to cross more and more things off that list until we see the signal we've been looking for. But so far, no great luck.
So where's all the antimatter?
Good question. So this is one of the most intensely debated topics in modern cosmology, or in the last several decades anyway. So if you just take what we know about the laws of physics, okay, you take all the stuff we learned from machines like particle accelerators and all the experiments we've ever done, and we tried to deduce from those laws of physics what our universe should look like today. Well, it really seems like our universe should contain equal amounts of matter and what we call antimatter. So what is antimatter? So for every kind of particle that exists, we find in nature there exists kind of an equal and opposite counterpart. So take the electron as an example. The electron has negative charge, but it turns out there exists an antimatter version of the electron that we call a positron. The positron and electron have the same mass. They have all the same properties, basically, except that positron has a positive amount of electric charge. Quarks have antiquarks. Every particle in nature has an anti-version of it, an antimatter version. And these things always get produced and destroyed in equal amounts. So I can't create an electron in nature without also creating a positron alongside it. And I can't destroy an electron and take it away from nature without destroying a positron alongside it. So the fates of matter and antimatter are closely intertwined. So one of the biggest challenges for the Big Bang is explaining how whatever went on in the very first fraction of a second that filled our universe with a hot bath of particles and energy, that presumably created equal amounts of matter and antimatter. How did we go from that state to the state we find our universe in now, where there's a lot of matter in our universe and very little antimatter? So whatever caused this to happen, we call it baryogenesis, but it's really just a placeholder name. It's just a word saying the thing that made this happen, and we don't know what it is. We have, kind of like dark matter, we have many, many different hypotheses for how this might have played out, but we don't know what the right answer is. And, I've written down my own theories, hypothesizing what might have happened. Other people have their own ideas. Again, I could probably come up with a new way to do baryogenesis before breakfast if I needed to, but it's hard to test. So we have a lot of perfectly experimentally viable guesses as to what might have caused baryogenesis to happen, and no satisfactory evidence at this point leading us to know which one was really what happened.
What do you think is the next big hurdle to be overcome that will lead to new discoveries in the field?
I mean, short answer is I don't know. We're trying a bunch of different things. A few things I'm really excited about, but I'm not sure they're going to lead to huge discoveries. But like the ones I'm keeping my eye on are some future gamma ray telescopes. So gamma rays are just really high energy pieces of light, photons with a lot of energy. And these are interesting for a bunch of reasons, but I'm especially interested in looking for dark matter particles using gamma ray telescopes. So I'm really excited about that. I'm really excited about the upcoming or next generation versions of telescopes that are going to study the light from the Big Bang, what we call the cosmic microwave background. These experiments will be sensitive to a bunch of theories we have in which there might have been exotic kinds of particles in the early universe. We can really find out if those ever existed for the first time. We can use these telescopes to study things like whether and how our universe might have kind of exploded in a ultra short, intense era of expansion at early times, what we call cosmic inflation. It can do a lot of interesting science that we don't have good answers to. I'm also really excited for a bunch of detectors that are going to try to detect cosmic ray particles that are made of antimatter from space. So I'm excited about an experiment called GAPS, which is going to fly in a series of balloons over the next few years. It will look for things like antiprotons, anti-deuteron nuclei, and anti-helium nuclei, these sorts of things that so far we haven't really been able to understand or figure out if those things are present. And if they are, they could tell us things about dark matter, among other open questions. So lots of things going on. I just mentioned 3, but I could give you 30 if you had all day.
Gotcha. Ifan asks, is dark matter equally dispersed throughout the universe, or is it clumped together much like gravity causes matter to attract?
Yeah, it's clumped. It's not clumped in exactly the same way as normal matter made of atoms. It's like, as far as we know, we don't think there are any like planets or moons made of dark matter. Okay. The reason that ordinary atoms collapse into things like planets and moons, or stars for that matter, is that they have ways to like lose their energy and their momentum, their angular momentum. And that allows like a cloud of stuff to collapse into something dense like a planet. As far as we know, dark matter doesn't have that ability, and it seems to be more diffusely distributed throughout the universe, but it's still kind of clumpy. For example, like if you take our own Milky Way galaxy, the visible part of that galaxy has a big bulge in the middle, which is a dense combination of stars and gas. And then there's a big disk that extends tens of thousands of light years along that plane. And then that whole thing is embedded in a big cloud of dark matter. We call it Milky Way's dark matter halo. And that halo goes on for hundreds of thousands of light years. So it's much bigger and more diffuse than the visible part of the galaxy, but it's not the same everywhere. So there are these big halos. Those are big clumps of dark matter that fill our universe. And right now we're in a place that is hundreds of times more dense than average in dark matter compared to the whole universe, which is mostly devoid of anything.
So is it also affected by gravity?
Sure. Yeah. Gravity, as far as we know, works on absolutely everything. That's kind of a built-in assumption of general relativity, the theory of gravity that Einstein proposed. So yeah, we think absolutely everything, including dark matter and atoms and everything else, experiences gravity.
What do you think about the fine-tuning of the universe?
Yeah. So there, in general, if you have a theory and your theory only works or only agrees with observations if you have to tune specific parameters to an extreme degree, then you get suspicious of that theory. Okay. So, for example, let's say I told you I have a theory where it says the number of books on my shelf is equal to the number of grains of sand in all the beaches in the world minus all of the dogs that have ever lived. Okay. All right. So 2 really big numbers. I'm going to subtract them and I'm going to get, I'm at 30 something books or something on my shelf. Okay. That would be a weird coincidence. And it would make me think that my theory is probably nonsense. Okay. So in physics, things like this sometimes come up. So, for example, there's something we call the cosmological constant, which is a number that characterizes how much energy exists in empty space. Okay, it's like a vacuum energy that fills all of the universe. And Einstein's theory, general relativity, says that you can have a cosmological constant, you can have this vacuum energy, but he doesn't give us any reason to think that number should be bigger, smaller, whatever. It could be any number. But when we make calculations using what we call quantum field theory to estimate how big this number should be, we get that the number should be really, 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 really big, like 10 to the 120 times bigger than we measure it to be. Okay, like in 10 to the 120, that's a big number. Just try writing that out 10000 times. It's an exceedingly big number. So we're extremely wrong. Okay, what we're doing has to be wrong. So what's the answer to this? Well, it turns out that different particles can interact with the universe in a way that can give you either positive or negative contributions to this. We think all of these contributions are going to be this 10 to the 120 number or so, but some of them will be positive and some of them are negative. So maybe the positive ones cancel almost perfectly with the negative ones, leaving with this very, very small number behind, like subtracting the number of grains of sand from all the dogs that have ever existed or whatever. And I'm just making that example up. I have no idea how many dogs existed or if it's similar to the grains of sand, but for sake of argument, let's say it is. So in that case, you might be able to explain why our vacuum energy density or cosmological constant is small, but it seems really fine-tuned, and it leaves a lot of physicists thinking that's the wrong way to think about it.
So you don't think it's a god did it? That's not the best explanation.
You might be asking the wrong guy for that. I'm pretty much a straight up, naturalist materialist. I have respect for a lot of people who are theologically inclined, but I don't happen to be one of them. I don't see any evidence for such a divine being or designer. The more I look at the universe as a physicist, the more it seems arbitrary, and the more it seems pointless and meaningless. That doesn't mean human beings can't derive meaning or impose it themselves. But I don't see anything about the structure of the universe that makes me think this looks like it was put here for any grand overarching purpose.
Do you think there are new laws that we haven't discovered yet that could potentially entangle different forces and constants that we see, kind of like how we discovered the weak and electromagnetic force are connected at high enough temperatures? And do you think that there are more connections, like the grand unified theory, that many of these laws may be interconnected in a way we haven't discovered yet?
So, like a lot of physicists, I think grand unified theories are a pretty compelling hypothesis or series of hypotheses. Basically, the idea is like in the Standard Model of particle physics, there are three forces. There's the electromagnetic force, the thing that's responsible for electricity and magnetism. And then there's the things we call the weak nuclear force and the strong nuclear force. The strong nuclear force holds together quarks and gluons in the nuclei, and it holds nuclei together, into protons and neutrons, and it holds protons and neutrons together into nuclei. The weak force is responsible for certain kinds of decay and like neutrino interactions and things like this. These forces seem to be totally different from each other in the Standard Model. They have nothing to do with each other, but they're each described by a thing we call a gauge symmetry. It's a mathematical idea, but the gauge symmetry for electromagnetism we call U1, and the one for the strong force is SU3, and the one for the weak force is SU2. What I just said is approximately correct. It's technically not perfect, but for this discussion, I think it's fine. So it turns out that so it just seems like there are three random things kind of glued together. It looks a little ugly and Baroque for no particular reason. So grand unified theory say, no. There's really just one big gauge group. It's a bigger gauge group. Maybe it's something like SU5. That's one of the ones that are popular. And it turns out that inside of the structure of this mathematical thing we call SU5, there fits the U1, the SU2, and the SU3 that we've already discovered. So that would mean that aren't really these three separate forces. They're all different facets of one grand unified force. But probably since the very, very early universe, shortly after the Big Bang, that unified force was broken. That symmetry was broken in such a way that we experienced three forces. But if you were to run things backward in time and recreate the hot conditions of the Big Bang, you would see that deep down, all three of these forces are really manifestations of the same thing. Now, to be clear, we don't have any evidence of this, or at least not any overwhelming evidence. One of the things that these theories predict is that protons should very, very, very slowly decay. And we're actively looking for evidence of that. We haven't seen any yet. But if we were to see protons decay someday, that could increase the interest and enthusiasm for these grand unified theories.
Do you see the same kind of pattern in the fine structure constant, 1 over 136 or whatever, in many different patterns of everything, all the different things we see that don't seem to be related in any way?
Yes, so the fine structure constant is basically a number that characterizes how strong the electromagnetic force is. So it turns out it's just a coincidence that it's approximately 1 over 137. It's not exactly 1 over 137. Earlier in the 20th century, it seemed to be exactly that. And people, when you see an integer in your theory, you're looking for an explanation for that integer, right? But I forget what the real number is, but the real number is like 1 over 137.08932, whatever. And that's, so it's just a coincidence that it was close to 1 over an integer. So I don't see any particular magic there. That being said, I do, aspire on behalf of the, institution of physics, that one day we might have a theory where all of these parameters, which we just measure now, could be explained. So the standard model of particle physics has 17 different free parameters that are not predicted by the theory. So how massive is the electron, or how strong is this force, or et cetera, et cetera, et cetera. These are just things we have to go out and measure. I would much prefer to have a theory that told me this has to be this number, or this has to be related to this in this way. That would be a more powerful theory, and one that I would be enthusiastic to discover one day if that were in the cards. But so far, no such theory has been forthcoming.
So I recently read a poll of physicists about, I forget what it's called, it's the fundamental attitudes towards quantum mechanics, something, something by Schlosshauser. And it added, the first question was about randomness. And is randomness just apparent, like a hidden variable kind of thing, or is it irreducible, or is it fundamental to reality? What is your position on randomness?
So in the context of quantum mechanics, physicists have a huge diversity of opinions. Okay, so and it has been changing over time. Like several decades ago, well, okay, let me back up and explain like where the origin of all this debate is. All right, so there's this weird feature in quantum mechanics, as originally described, is described in most textbooks. And basically, the premise is that in some state out there in nature, a given particle, let's say an electron, isn't in one place at one time, and it's not, doesn't have one amount of energy, it doesn't have one amount of speed. When an event happens, it doesn't happen at uniquely one time. All those things have many values spread out. So, this electron is here, 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 and here all at once. It has this variety of speeds all at once. If it does something, it does it at a whole bunch of different times. It carries a whole bunch of different kinds of energy. We characterize all this by the wave function of the electron. Okay, so very, very weird stuff. But we know that when we measure an electron, we find it to be in one place. So we have invented this idea, what we call the collapse of the wave function. So the electron has some wave function. It has a bunch of different locations, a bunch of different states at once. You make a measurement, and upon the act of measurement, it collapses into one particular state. That's what we measure, and we call this the collapse of the wave function. So I, and many other physicists agree with me, think that this is like really problematic philosophically. After all, like, what is it about the act of human observation that would collapse a wave function? After all, when just some electron undergoes some normal interaction with something that doesn't involve a human observer, it doesn't collapse the wave function. So then I have to ask questions like, well, okay, what's special about my observation? Like, can my dog collapse a wave function? Is he conscious enough to do it? Can a flea on the dog? Can an amoeba on the flea on the dog do it? There's no good answer to this. So I would argue that there's some deep down reasons to be skeptical that wave functions collapse. So if they don't collapse, what do they do instead? So a way to explain this is with this classic example, the Schrodinger cat thought experiment. So no one's ever done this experiment. It's not the sort of experiment you go to the laboratory and do. It's more of an illustration to help you think through the weirdness of quantum mechanics. So the idea is this. I have a box. It's an impenetrable box. I put in that box a vial of poison hooked up to a radiometer and some radioactive material. And I set it up so that after an hour, there's a 50% chance that this quantum mechanical process will happen that will cause the vial of poison to open and fill the box. Now I put a cat in the box and I close the door. I wait for an hour. According to the old way of thinking about quantum mechanics, the wave function collapse idea, before you open the door, the poison is in a superposition of broken and intact states, and that means the cat is in a superposition of alive and dead states. Notice I'm using the word "and" here. The cat is alive and dead, not or dead. Okay, so it's very, very different than your normal pre-quantum intuition. But according to quantum mechanics, that the universe exists in a superposition of states in which the cat is alive and dead. The old way of thinking about quantum mechanics is you open that door, the wave function of the universe collapses, and the cat now becomes either entirely alive or entirely dead. You go from a superposition to a singular state. But now let's say wave functions don't collapse, because like I said, they're pretty philosophically untenable. So maybe instead I open the door, and when I'm done, the universe is still in a superposition, but in one part of the universe, there's me looking at an alive cat. And in another part, there's something just like me seeing a dead cat. So now I become part of the superposition. So the old way of thinking about it, the way in which where wave functions collapse, is called the Copenhagen interpretation of quantum mechanics. And the version I'm describing is called the many worlds interpretation of quantum mechanics. And basically where we disagree is whether, when one makes an observation, does the superposition of the universe go away, or do we become part of it? Okay. So I would say these days, more and more physicists are at least open-minded to the many worlds interpretation. Many are active proponents of it. And I tend to find myself in that category. I mean, I don't really care if I convince anybody, because I think both versions of the theory make the same predictions, and they both do perfectly well for science. So it's not really essential that we come to agreement on this. But philosophically, I think the many worlds view works a lot better, or has a lot more appealing features than the Copenhagen view. And now connecting this to randomness, whereas the collapse of the wave function is a fundamentally random process. You have to decide which part of the wave function survives the process of collapse, and that is fundamentally random. In many worlds quantum mechanics, there's really nothing that's random. Every quantum possibility happens 100% of the time. So there's really nothing random about that. It's completely deterministic. The laws of physics, namely the Schrodinger equation, just keeps moving forward through time, predicting exactly how the whole quantum multiverse will evolve. So maybe there's no randomness in the universe, even though it feels like there is quite often.
Gotcha. And do you feel no intuitional pull against the idea that if the many worlds hypothesis is true, then every possible universe exists somewhere? So there is a you with blue skin and a you who believes everything that's the opposite of what you currently believe, and they all exist simultaneously at the same time in some universe?
No, that doesn't bother me at all. The universe is a big place. No, I mean, it strikes me just as weird as it strikes a lot of people, but no, I wouldn't say it doesn't cause me any stress. Not anything deep down.
All right. I recently had an email exchange with somebody talking about, is it possible for a particle to exist at absolute zero? Obviously, we can't get to absolute zero, but if we could, would a particle still exist, still be there?
So temperature, absolute zero in this case, is a measure of how much energy that particle has. So we define absolute zero as just like the lowest energy state that something can hypothetically exist in. So yeah, you could do that. But a lot of weird things happen when you do that. In particular, so when you, according to these laws of quantum mechanics, there's something called the Heisenberg uncertainty principle, which says the amount of momentum that something has, the quantum uncertainty, the range of momenta its wave function has to cover, multiplied by the range of locations it has to cover, has to be bigger than a particular number, something we call Planck's constant. So if we're really going to suck all the energy out of this thing, so basically we're saying it has as little momentum as allowed then the quantum uncertainty in its location gets big. So that wave function starts spreading over more and more space. And so something that's close to absolute zero is going to be kind of infinitely spread out over space, at which point you can't really even talk about where it is. It's just kind of everywhere all at once.
Gotcha. So it would exist sort of, but everywhere all at once.
Yeah, I mean, and then there are some complications too because the universe is expanding and all this, and it can't really be everywhere. But yes, approximately something like that.
So what is your view on virtual particles? Do they exist? How do they exist? What is your view on the Casimir effect?
Yeah. So what I would say is, well, let me say what a virtual particle is first. So if we have a situation where, I don't know, I'm going to take 2 electrons and bounce them off each other, and I want to calculate how much that should happen and what, I want to calculate everything about that process. Well, it turns out to do that, you need to calculate a whole bunch of things we call Feynman diagrams, which show different ways in which these things could scatter. Like the simplest one is the 2 particles, the 2 electrons pass 1 photon back and forth. This is a virtual photon. And when we get that, we can calculate how much they scatter. But also there's a smaller chance that, a photon will travel from one to the other, briefly become an electron-positron pair, become a photon again, and then interact with the other electron. And you can go more and more complicated and build up more and more complicated Feynman diagrams. And it turns out if you want to get the real right answer, you need to include all of these, okay? And when you do that, it works. You get the right answer. You can make correct, empirically, experimentally verifiable predictions. So what I would say is that, like, if you want to pretend that virtual particles don't exist, you're going to get the wrong answer, when you do these calculations. So in that sense, they exist. On the other hand, like, just because some object or entity is useful in your scientific theory doesn't necessarily mean it deep down exists. Okay. The example I like to give is, like, 2000 years ago, astronomers had, ideas about big spheres that were orbiting or rotating, carrying stars and planets with them. And they had spheres on tops of spheres rotating in complicated ways and whatever. And these theories worked really well, or at least for the time, given the technology of the time, they worked very well to help you build a reliable calendar and to predict when eclipses would happen and all sorts of things like this. But those things don't exist, not really. So they're useful. It's a good thing they included those objects in their theories because it made their theories accomplish more of what they were trying to do with them. But deep down, those objects don't exist. And maybe someday we will have a different theory of particle physics or whatever that doesn't contain all of the same objects that our current one does and will work just as well or better. I'm totally open-minded to this. So in my mind, the deep down goal of science is to make a theory that makes predictions that are as accurate as possible, as often as possible, about as many things as possible. And right now, those theories contain descriptions of virtual particles. It doesn't really matter if they're quote unquote real or not. But you definitely don't want to ignore them. You don't want to do quantum field theory without virtual particles. You will get the wrong answer every time.
What do you think is the fundamental nature of reality? Do you think it's information, relations? What is energy made of?
That's a really good question, and I wish I had a good answer. It's a question I spent a lot of time thinking about. But I sometimes teach a class in the philosophy of cosmology or philosophy of science in connection to cosmology at the University of Chicago. And in that class, I tell my students that, like, sometimes I wake up on a Monday with one opinion on this, and then on Tuesday I wake up with a completely different opinion. So I think I know all the main arguments. I think I understand them, and they all have their strengths and weaknesses, and they've left me uncertain. But, like, for example, a question I've been thinking about a lot lately, I've been reading a lot of books about this lately, has to do with what is the the nature of mathematics? Is this something that we discover, or are mathematical truths something we invent? Okay. And like, I'm pretty convinced that if we one day met a alien species that has built technology, enough to either visit us or communicate with us or whatever, they'll have ideas about mathematics that closely correlate or map onto the ideas we have in mathematics. They'll have something that looks like our number pi. All right. And maybe it won't be in base 10, so they won't be 3.14 or whatever, blah, blah, blah. But there'll be some ideas, this number, which they've realized is the ratio of different geometrical things and whatever. And they'll have concepts of number, and they'll a lot of the different mathematical constructs we've come up with, they'll have too. But does that mean we both discovered something? I don't think we discovered anything about the universe with mathematical discoveries, but we also didn't seem to invent it, because you can't independently invent things, without causal connection, and we don't have that. So I tend to think that really all we're doing when we do mathematics, and I'm sorry if you're a mathematician out there and disagree, I'm not trying to disparage anything here, but I tend to think all mathematics is just using something that you could characterize as logic to boil down relationships between ideas. And they're really just tautologies. There's things that had to be true if you thought about them clearly. You can't write down a circle in Euclidean geometry that has a different ratio than pi for circumference to its diameter, right? Things like this, it just had to be that way. It wasn't something, you can't imagine a universe in which it's different, because such a universe would be logically inconsistent. So that's where I think about math. Now, when it comes to the physical world, we have a different epistemological access to that. What I mean by that is that we have actual ways of finding out things about the universe that don't just rely on us thinking about things. And namely, we have observations. We can apply the scientific method to the universe in a way that we can't do that to math. Everything we know about math, we know purely because we thought about things. We can't do any experiments to test math. But science, we do experiments to test. And then we use math or logic to refine what those experiments or measurements say and don't say. So there seems to be something that we're connecting with when we do experiments, some universe, some world that's out there. Maybe we're all living in something like the Matrix. I'm fine with that, but that's still a world. It's a virtual world, but there's some sort of world. And we measure things about that world and try to figure out the relationships to different things in that world. I think that's all we can really hope to do in science. Maybe that's like a physical deep down thing. Maybe that's a relationship of a bunch of different bits on a computer somewhere. I don't know. I'm not sure it matters. I'm kind of happy living in a virtual world as much as a quote unquote real one, as long as it seems real to me. Awesome. I ranted for a while there. That was kind of I went off the rails a bit, but I hope someone out there enjoyed it.
For sure. We have lots of comments that actually say they're enjoying the conversation. So I do appreciate that. What is your position on observer collapse? Because you mentioned that earlier. You said the collapse only happens when we look at it. Do other things cause collapse? Can simply instruments and measurement devices cause collapse? Or does it require a conscious agent? Does the cat cause collapse in the Schrodinger experiment?
Well, those questions I don't think have any good answer, and that's why I just don't think wave functions collapse. I tend to take the position that wave functions just stay wave functions. They evolve, they never collapse, and that leads you to the many worlds version of quantum mechanics. So, if you're a physicist out there and you have a different opinion, by all means, use Copenhagen. It will give us all the same answers for everything. I have no ill will towards the Copenhagen advocate, but it doesn't make sense to me. I think the many worlds is much more compelling.
You say something like, well, you're just all wrong if you disagree, and I can clip that. I can put it on YouTube, get lots of views. It'd be great.
No, I say it like it is, and I don't really care that much. It's definitely the sort of thing that I've debated with my colleagues over a beer many times, or for many hours. I enjoy the conversation, but there are things I actually want to change their mind about, and this isn't one of them. It's not probably the single most popular opinion on these sorts of issues among physicists is the opinion known as, quote, shut up and calculate, which is basically saying, who cares which one of these things are right? You can use either one to calculate the right answer. We can test that answer in an experiment, and it doesn't matter which philosophical school you fall in. So stop debating it. I don't share that view because I think it's a lot of fun to debate these things. But they're right. It's not a scientifically relevant question. Maybe it's a philosophically relevant one, but I'm a little bit of a philosophically minded scientist, so I'm okay in that state.
You mentioned that there were some things you want to change their mind about, such
Sure.
as.
I mean, scientific things, so there are, there might be a debate about whether some experiments data means X or means Y. And if I think I figured out the right answer, and sometimes I feel I have, and they think the wrong answer, I want to show them why I think the answer is right, and show them the calculations or the data or the arguments or whatever. I mean, we all do this all the time. Otherwise, we wouldn't make much progress. But we evolved towards consensus based on, reasoned persuasion.
Was there a particular example right now that you do want to convince your colleagues that they are wrong about, that you are particularly passionate about?
Yeah. Okay. So what's the best example right now? Yeah. Okay. So there's this signal of gamma rays that we've discovered coming from the direction of the galactic center. I found this in the data from a telescope called the Fermi Gamma Ray Space Telescope back in 2009, working with a student at the time named Lisa Goodenough. And then we confirmed it with several subsequent studies, and other people have confirmed it since then. So no one's really debating whether the signal is there anymore. But it took years of this sort of reasoned persuasion to get everyone on board with that. But that debate we've won. Now the ongoing debate is what makes the signal. So I think it's likely that this signal is produced by particles of dark matter, which, if true, would give us some important insights into what dark matter is made of. So it would be important if it were true. And then other people are arguing that no, it's probably not coming from dark matter. It's probably coming from a large number of objects we call pulsars. So a pulsar is something called a neutron star, which is like basically a chunk of matter with a mass similar to the sun, but the size of like a city. Okay, it's like 10 kilometers across, and spinning super, super fast on its axis. So super dense, super rapidly spinning object. And these things can make gamma rays, and some people have argued these gamma rays are coming from a bunch of pulsars. So I think there are a lot of good arguments to be made against the pulsar hypothesis, and I will passionately argue those in my talks and in conferences and in papers I write. I think the enthusiasm for pulsars is a bit misplaced, and more people should be spending more of their intellectual energy trying to hunt down this dark matter picture and try to figure out, try to confirm that this is in fact dark matter particles that are responsible. And once we've confirmed that, use that information to learn everything we can about the dark matter.
So 2 questions. How can dark matter create gamma rays? And how does a collection of pulsars create a single gamma ray?
Good. So let me answer them in reverse order. So each pulsar makes a bunch of gamma rays. But now imagine that you have a big cloud of pulsars, like tens or hundreds of thousands of pulsars. It will just look kind of like a big cloud of gamma rays. So kind of like the Milky Way is made up of a bunch of stars, but you get out in a good dark night with not much cloud cover, and you see just a diffuse haze of light across the sky. That's just because you can't resolve the individual stars. So here you can't resolve the individual pulsars, at least not very easily. That would be the idea. So with the dark matter, in a lot of theories, the ones we talked about before, that where the dark matter is something we call a WIMP, weakly interacting massive particle. Individual pieces of dark matter will be stable, but when you have 2 of them and they come in contact, they can be destroyed, having their energy transformed into other sorts of stuff like gamma rays that we can hope to see. This doesn't happen very often, but in places where the dark matter density is high, this sort of dark matter annihilation could potentially lead to observable signals like the one we've seen here.
How much dark matter would have to collide to create like gamma rays are like the most powerful signals we have in the universe, right? So does it take a significant amount of dark matter to produce that?
So when two dark matter particles annihilate, they will make typically several gamma rays in that single event. Okay. But to produce enough gamma rays to explain the signal we've seen, there would have to be a lot of these particles. So fortunately, we have ways of estimating how much dark matter there should be there, and we should have ways of estimating for these class of candidates we call WIPs, how often they should do this, and all this matches pretty well with the brightness of the signal we've seen. So if you imagine that the dark matter particles were created in the Big Bang, like we usually do, and that they interact at the kind of rate you would expect based on how much survived the Big Bang, then they should produce a gamma ray signal that's about as bright as the one we've observed.
So I have a tendency to prefer theories that have more combinations of things that have already been demonstrated to exist, and so I intuitively feel like the pulsar explanation, because we know pulsars actually exist,
Yeah.
is more like simplistic. It's simpler hypothesis, less entities posited that we don't need. Why do you think that would be less prudent in this case?
Yeah, good. So and based on what I've said so far, your reasoning is right on. You just applied Occam's razor. It says, if you can explain all the data with stuff that you already know must exist, then you shouldn't posit anything else. Right. So, but there are things that make that hard, that make it less likely in this case. So first of all, we haven't actually seen any pulsars in the galactic center. And if the pulsars there are like the pulsars we see elsewhere, then we should have seen some of them already. The brightest ones our telescope should have detected. So the pulsars in the galactic center would have to be dimmer on average than the pulsars elsewhere. Also, where we find pulsars elsewhere, they tend to be accompanied by these bright X-ray emitting things that we call low mass X-ray binaries. And we don't see very many of those in the inner galaxy, in the galactic center. So that makes us think there aren't many pulsars there, not enough to explain the signal. Also, there's just a simple fact that, like, if you try to estimate how many pulsars we think should have formed in the galactic center, it's not enough. Okay, so you'd have to posit that for some reason way more pulsars were formed than we thought there should have in the galactic center. They, for some reason, aren't accompanied by these X-ray emitting sources, and for some reason, they're systematically fainter than the pulsars we see elsewhere. So all these things kind of put together, gives you some reason to pause and think, well, maybe it's not positing something that we know exists. This is really positing something different, some completely new kind of pulsar that evolves differently, that behaves differently. So it's a little more exotic than I think Occam would be happy with.
So would we expect to see the same kinds of gamma rays in any location that has an equally sufficient amount of dark matter in the universe?
Yeah. So it turns out that because of our proximity to the galactic center and the amount of dark matter there, that should be the single brightest place. But we have all these things called dwarf galaxies, which are like the small mini galaxies that orbit the Milky Way. And there are, probably hundreds of these. We've discovered more than 50 of them. And these things should give gamma rays. If dark matter is producing the signal, then these dwarfs should give gamma rays that look a lot alike. But we just don't have telescopes that are quite big enough yet to see it. I'm a big proponent of building a telescope kind of like Fermi, but maybe substantially larger to test this hypothesis. It should be very clearly capable of resolving this debate once and for all.
How big would it have to be compared to like the James Webb? And would it be better in space than on ground, obviously, right?
Yeah, you can't do this sort of astronomy from the ground, unfortunately. Gamma rays hit the top of the atmosphere and never make it to the bottom, right? So never make it to the ground. So in this sort of energy range, you definitely need to go to space. So the Fermi telescope was something like a meter in its detecting area from side to side. I would like something that is maybe, I don't know, 3 meters from side to side, or 2.5 meters side to side, something like that. So it's a pretty big chunk of hardware, but we have the rockets to do that now. We didn't back in the day. Rockets are getting bigger and frankly cheaper. That's important. James Webb is a totally different animal, much, much more expensive than what I'm talking about here. But the JWST was an important instrument that's going to do a lot of great science. But it's that what they're doing with that is it's a much harder task than just building a big gamma ray telescope. Big gamma ray telescopes aren't easy to build, but compared to JWST, yeah, this would not be nearly as costly or as difficult.
Gotcha. We got a question from Samir. He asks, could one new discovery eliminate all existing overlapping theories and send us back to the drawing board, whether in physics or astrophysics?
So this has happened before in the history of science, right? So, I think if you were a physicist in 1905, you probably thought you had things pretty much wrapped up, right? Basic like Newtonian ideas about physics, forces, mass, velocities, momentum, all this stuff had been around for a couple hundred years or a few hundred years. And every discovery we made just fit neatly into that paradigm over and over and over again. Then Einstein comes along in 1905, introduces the first ideas that would become relativity and the first ideas that would become quantum mechanics. And those things weren't just gentle revisions of Newtonian physics. They were a complete revolution, two of them all at once. So, I hope that happens again. This would be fun, right? I would love to see everything I know about physics be overturned and see that play out. Even better than being able to see it, I would love to play a part in it. If I can ever be so lucky. But all we can do is keep plugging ahead and hoping that happens. I guess I'll take whatever kind of progress I can get.
Yeah, the Hubble example comes to mind, where we discovered that all the universes or galaxies were traveling away from each other and increasing in speed.
Yeah, all that was tied up with Einstein's relativity too. Like, we didn't have any way of even talking about what space and time would do, or how the space could be doing something like expanding. Before Einstein, we never used any verbs to describe space, right? Can you imagine before Einstein saying that space was going to do something? Space didn't do anything in the Newtonian paradigm. Things moved through space, but it was the things doing the moving. Einstein taught us that space and time themselves can be the actors. They can bend, they can curve, they can warp, they can expand, they can contract. And it was then Hubble, a little more than a decade later, who actually saw the evidence that was really going on.
Well, Samir, I know, is a very religious commenter, and so one of the arguments people use in the religious context is, oh, well, you can't trust science because it changes all the time.
We are a self-correcting institution, and you shouldn't pick up any textbook on science and think everything in this book is going to be, viewed as correct 1,000 years from now. I'm sure there are things that are going to be considered incorrect in there, or at least refined, okay, if not outright incorrect. Newtonian ideas of force and stuff aren't exactly wrong. They're just like incomplete. They're not the whole story. And we've added to that story and made it a lot richer with discoveries in the 20th century. But yeah, we never try to make claims of absolute correctness. That being said, I think it's the best tool we have to approximate truth. And if you want to know something about our universe, and I'm using those words carefully, but if you want to know something factual about our universe, there isn't anything better than the scientific method to get at that answer.
There's a question from Travis. He asked, how religious are your coworkers? Because that's a big common debate, a lot of religious people. And we talk about how in the higher level academic fields, very few are religious.
I wouldn't go as far as to say very few, and there's a huge diversity, right? So among my closest circle of coworkers, I can think of, and I'm talking maybe 5 or 10 people. I can think of at least 2 who I would call devotedly religious, they accept all the tenets of modern science, but they don't think that's incompatible with, in their case, their Christianity, but it could be other religions too, I think. and I have no quarrel with any of that. That sounds fine to me. But you know, you don't find many scientists who are, for example, young Earth creationists or something. But you do find plenty of scientists who, you know, they read the Bible and they think there are important truths in there, and they accept the theological tenets of their religion. But yeah, there are probably more scientists who are atheists than among the general population. But I don't know, maybe like twice as many or something, not 10 times as many. Would something like that would be my guess. I haven't actually seen any scientific surveys on this, but just from my own personal experience.
I've seen several. There's one about the Royal Institute and the National Academy of Sciences that show the percent of atheists is in like the 90-something% who would believe in like a interactive deity in the universe or something like that.
90-something%. Okay. All right. Well, that surprises me, but you know, I guess it depends who you're surveying and things, but and how you phrase the questions.
Yeah.
Yeah. Okay. I'm surprised it's that high. That's not been my experience.
Yeah, in philosophy, there's one that shows that among academic philosophers, it's 70-something% are atheists, I think. So in the really super high academic Nobel Prize level range, it's
No.
leans more towards the atheist range, like the higher up you
Yeah.
go.
Yeah. I suspect there's something to that. I think at at Harvard, the distribution might look pretty different from, you know, the University of, you know, I don't want to name
Yeah,
I don't want to call anyone out as being the opposite of Harvard, but I think you can picture any number of schools.
Leo has a question. Are there any academics in physics or cosmology that look at the evidence and conclude that the Earth is flat? I think, or not
No.
flat?
No.
What? No
there
flat
are not.
earthers?
No, I've literally never met a scientist who was a flat earther or even thought there was anything to talk about.
That's so sad. It's surprising. I don't know why. Samir has another question. Thank you for the super chat. Since we sent a probe to Pluto, has anyone thought of landing a telescope there for a massive 12 light hour parallax?
So I mean, it's certainly something that I think we have the technology we, you know, could do if we wanted to spend our resources on that. This sounds pretty cool to me. It also sounds expensive. Landing things on planets is a lot harder than doing a flyby. And so far, you know, we basically limited those sorts of things to the moon and Mars and stuff. But yeah, I think like, I mean, that might be science fiction, but I think it's like realistic science fiction. We could do that. I would tune in to watch that for sure.
Do you think we could learn anything new from doing those on faraway planets?
Yeah. So the what the questioner is referring to is this thing called parallax, which is basically a geometrical way of measuring distances. So if you put a really good telescope on somewhere like Pluto, it could measure distances in a pretty great way. But I haven't crunched the numbers, so I don't know what kind of telescope you'd really need and if that's realistic. But it's an interesting idea. I'm not in a position to dismiss it out of hand. I'll say that for sure.
Gotcha. Mr. Kreening asks, does Professor Hooper think we will find selectrons and squarks eventually?
All right. So this is asking about a theory called supersymmetry. So, you know, when I was a grad student in right around 2000 or so, a lot of particle physicists, maybe even most, really took seriously a theory called supersymmetry, which said that for every kind of particle we know about, there would be a kind of a flip version. It's not antimatter, it's different from that, but every boson has a fermion and every fermion has a boson. It has to do with how much angular momentum they have and stuff like this. So, and the selectron, as their question says, is the superpartner particle of the electron. Squarks are the superpartner particles of the quarks, and so on and so forth. So, I mean, I've written a lot of papers on this theory. I think the theory is very, very compelling. In fact, I wrote a book about this theory back in, 2008 or something, called Nature's Blueprint. And, you know, I think I wrote in that book, in fact, I know I wrote in that book that I think there's a 50-50 shot that the upcoming particle collider, the Large Hadron Collider, would discover these particles. Okay. So that's not very committal. It's kind of a intellectually cowardly thing to say. You can't be wrong if you predict it's 50-50, but that's what I said. And we haven't seen them. Okay. So certainly I think now it is less likely than 50-50 that the stuff exists. Okay. I used to think it was, 50-50, this thing would be able to see it. But so now, I don't know, maybe I think they're just beyond the reach of this machine and we'll discover them eventually, but not quite yet. But also it's very possible that this theory just doesn't get manifest in nature, at least in the ways that we've imagined. There are a lot of good things about this theory, a lot of reasons we took it seriously, a lot of reasons we got excited about it. The theories we find compelling, we find compelling for reasons. And this one does a lot of stuff that we like. But, if the data don't support it, then it's not true. And so far, I would say the data have not supported this theory. And a lot of people have moved on and are thinking about other things instead.
Gotcha. Brian Stevens asks, does he believe axions solve the strong CP problem?
All right, so a lot to unpack here. So CP stands for charge parity. And basically, like the electromagnetic force completely respects a symmetry called charge parity. So basically, if I took the whole universe at one moment in time, I turned all the positively charged particles into negatively charged particles and vice versa. And I changed the parity, like which way the particles are spinning. So if something's spinning clockwise, now it's spinning counterclockwise and vice versa. If I did that all at once, everything would look fine. The laws of physics would apply to them in exactly the same way that they did before the transformation. And like I said, electromagnetism respects this symmetry. The weak force does not. And in fact, it kind of maximally violates it. So that's kind of interesting. And then the strong force, we look at that force as it appears in the standard model of particle physics, and there's nothing about the structure of that force that leads us to expect that CP should be conserved. It should be violated in the strong interactions. But experimentally, it doesn't seem to be. We don't see any evidence of CP being violated in the strong interactions. This is really weird. So there have been various theoretical proposals to try to explain this. One is called the Pesce-Quinn solution for Roberto Pesce and Helen Quinn. And this is a complicated theory involving broken symmetry and a whole bunch of other stuff. But the important thing is that it predicts that there should be a very light and very feebly interacting particle called an axion. And so in this particular theory that explains the strong CP problem, you get this thing that should exist called axions, and maybe axions make up the dark matter, which is why a lot of us study axions. I wouldn't say that I quote unquote believe that axions solve the strong CP problem, but I've written papers on this. I take it seriously. I think it might, and I think we should experimentally find out whether it does.
Gotcha. Dylan Motes asked about, I like the idea of gravity becoming repulsive in the universe mass black hole singularity. So like the gravity becoming repulsive is from like the Guth early universe inflation theory. Is that right?
I think you're talking about the null energy conditions and stuff, I guess. Not super sure. I understand the question well enough to answer it.
Have you heard of Guth's early universe inflation, where at the early universe gravity was repulsive, caused the massive inflation?
Oh, okay, sure. Okay, yeah, okay, I understand now. Okay, okay, thanks. So, okay, let me unpack inflation. All right, it's fresh in my brain. I'm writing a textbook right now, and I'm currently working on the chapter on inflation, so it's all very fresh. All right, so our universe is weirdly uniform on cosmological scales. If I look in two different directions of the sky and I look at two like really, really big boxes, I'm talking about billions of light years across, they'll both have very similar numbers of galaxies. It doesn't look clumpy. I mean, it looks clumpy in small scales, but in large scales, it looks really, really uniform. And that's not what the Big Bang, as it was originally envisioned, predicted. Also, our universe's geometry is what we call flat. What I mean by that is like the laws of geometry or the rules of geometry you probably learned in like 9th or 10th grade or something, like the angles of triangles add up to 180 degrees and things like this. All of those things apply in flat space. But the Big Bang Theory, as originally envisioned, tends to cause a universe to become more and more curved as it expands. And it's been expanding a long time, so it should be really curved by now. And it's not. Okay. So these were two big problems that in the 70s people were wrestling with, or starting to become aware of, I guess. And then in 1980, Alan Guth and then others shortly thereafter started writing down theories of inflation to solve this. So the idea is that in the very, very early universe, tiny fraction of a second after the Big Bang, the universe grew exponentially, and that caused the universe to become flatter and to become more uniform. So you can explain these two features using the Big Bang Theory if you include this little period of inflation. I would say that in the decades that have passed, enough of the predictions of inflation have turned out to be true when we measured things. It has led most cosmologists to think that probably inflation happened. Not many of us will say we're sure, but it's definitely a standard part of the cosmological paradigm now. And I think we'd be surprised if something like inflation didn't happen, or at least most of us. Okay. So what made inflation happen is there must have been some sort of big vacuum energy, some sort of energy throughout all of space that caused space to expand exponentially. You can, in the sense that it's pushing the universe apart, you can think of this as repulsive gravity. That's not usually the language I use, but real cosmologists do, and it's perfectly fine. So yeah, it's possible that in that very, very early stage, the energy stored up in the vacuum of space just tore space apart, taking everything apart from everything else for something like 10 to the minus 32 seconds. And when all that was done, that energy was transformed into a hot bath of particles. And we have the hot Big Bang, as we classically talked about before the idea of inflation.
Awesome. What's your position on singularities? Are there singularities in black holes, the Hawking-Hartle model? And was there singularity at the Big Bang? And are singularities real?
Yeah, I mean, so general relativity certainly allows for singularities. And that's the theory we use to talk about this stuff. That being said, like, I don't know, it would be super plausible that, as you get closer and closer to the singularity, the laws of physics might change. Maybe some sort of quantum gravity theory comes into place, at which point we don't know what happens. And I would just say that I think it's responsible. I consider the most responsible thing I can do to be pretty agnostic and open-minded about whether there are real singularities in nature. I'm sure there are black holes, and we usually think about those things as having space-time singularities, but maybe they don't. Maybe they break down before that. If you take general relativity and run it backwards, you get to a Big Bang singularity. But maybe it breaks down before that too. So I'm pretty open-minded about whether there really are or are not space-time singularities in nature.
Bitcoin, where'd he go? Leonard Bitcoin, I think was his name. He asked, "What is the speed?" Liam Bitcoin asked, "What is the speed of gravity and like gravitational waves, and is it a force?"
So the what we call the speed of light is kind of a misnomer, because it doesn't have really anything to do with light. Historically, we did measure the speed of light before we measured these other speeds I'm going to talk about. But the speed of light is just the fastest that anything can move through space. Okay. So light happens to be made of massless particles called photons. So they travel at the speed of light. But every kind of massless particle will travel at exactly the same speed, the speed of light. And gravity is no exception. So gravity, the effects of gravity travel through space at the speed of light. Exactly the same as light.
I mean, is gravity a force?
Yeah, well, okay. You could think of it as a force. It's perfectly right. You can also think of it as the effects of gravity. Sorry, I don't mean that. The effects of geometry. So Einstein's general relativity says that when you put energy in space, once you know where the energy is distributed and how much of it is and where it is, you can work out what the geometry or shape of the space-time will be. And once you know that, you can figure out how things will move through that space-time. And even you can do all of that, ignoring anything that you would call a force of gravity, and you get things to move as if there were a force of gravity. Okay, so one way you can think about this is, the Earth seems to be moving on a roughly circular orbit around the sun. Before Einstein, we thought of this as the sun and Earth pulling on each other, keeping us in this orbit. But Einstein would say, well, that's not really what's going on. What's going on is the sun has so much energy stored up in its mass that it changes the geometry of the surrounding space-time. And then the Earth just moves along this circle, which is actually the shortest route through space-time. That is a quote-unquote straight line through the curved space. And then there's no force of gravity, thinking about it that way. But if you prefer to think of it as a force, that's also fine with me.
Gotcha. Lyle asks, thank you for the super chat. What is the probability that grant givers are deceiving science to hide the flat Earth?
0.
What? We could be like a brain in a vat. There's got to be like, it can't be 0. It's like 0.
Okay, sure. Okay. Yeah, I mean, small enough that I don't think about it. It's not even a big enough number to spend 5 more seconds wondering what the answer is.
Get Stanfield, thank you for the super chat. Why is it so difficult to reconcile the standard model and general relativity?
Good. Yeah. So he's talking about the problem of building a theory of quantum gravity. I'm going to do a little self-promoting advertisement. I do a podcast show called Why This Universe? And we recently did a whole series of episodes on this question. So go back a few months and you'll find one about why we need a theory of quantum gravity. And then there are 3 different episodes on string theory, which kind of build on that. Okay, but here's a short answer. When you try to do, so all of the forces of nature, other than gravity, we know how to calculate the effects of. And when you get to higher and higher energies, we know how to calculate this evolution, and this all works fine. And everything is, well behaved and logically self-consistent, all this. When you try to do the same thing with gravity, everything blows up to infinity as you go to higher energies or smaller distance scales. And we don't know how to make it hold together. So we know gravity, when made quantum mechanical, is a fundamentally broken theory. It doesn't mean it's not useful, but we should expect the theory to not work in really extreme environments, really, really high energies and things like this. So we want to build a theory that it will work, that will describe these environments. String theory is probably our single best guess, but far from conclusive. We have other ideas like loop quantum gravity and other sorts of theories out there too. And maybe it's something we just haven't even thought of yet. Who knows? But honestly, we don't know how to make quantum, including the standard model, and general relativity play nice together. So ultimately, we need some theory that can incorporate both of those both of those phenomena into something that's self-consistent, doesn't lead to infinities everywhere, and doesn't lead to logical inconsistencies.
Awesome. And last question is from Kanye Twitty and Boots Ken something or another. What are your thoughts on fusion technology, and does it break the laws of physics?
I don't think it breaks the laws of physics. The sun's undergoing fusion all the time, and that's where sunlight comes from. We're probably not going to do fusion in the laboratory or on Earth in the same way that they do in the sun. That's probably just not practical. The people working on fusion aren't trying to violate any laws of physics. They're just trying to use the laws of physics to generate energy. And as far as trying to predict when this will come to market or when this will be successful or something, I don't know. I mean, a lot of progress has been made, but I just don't know enough about it. I have no engineering chops. I haven't followed the successes carefully enough to have a prediction. I'm certainly hopeful that one day I'll see a world where we can generate most of our energy through cold fusion, but it's a while off. I sadly to say.
Cold fusion. Oh, that's a little. That's.
Sorry. I mean the kind of fusion we can do on Earth as opposed to the core of the sun. I don't mean like tabletop. I don't mean room temperature fusion. Just to be
Gotcha. Sorry
about that. That was sloppy.
I was like, whoa! So new science discoveries required for that one.
No. Thanks for calling me out of that. Yeah. I don't want to be on the record supporting that. Yeah, great. Thanks.
Totally, we'll definitely clip that and send it to all of your friends. But we have been going for about an hour and 20 minutes. It was great having you on. Wonderful conversation. Really appreciate it. Do you want to give
my pleasure.
References where people can find out more about your work?
Yeah. So if you're into books, I've got my most recent one's called At the Edge of Time. You can find that on Amazon or wherever you like to do book shopping, ideally in your local bookstore. Why This Universe is the podcast that I co-host with Shalma Wegsman. We put out an episode every couple of weeks, so check that out. And yeah, thanks, Tom, for having me on. This has been fun.
Absolutely. Really appreciate it. Thanks again. And I hope you have a wonderful rest